Okay, so our next talk is also from Google, which is sort of like the extension of what they just did. It's on scaling P4-based automated reasoning. So over to you, Ali.
So hello everyone, I'm Ali, again from P4-Based automated reasoning team, co-presenting with Meghana, who was an intern in our team this summer. So in this talk, we're gonna overview our efforts overview our journey developing P4 symbolic and basically highlight our efforts in improving the performance and coverage of this tool. So I'm gonna start with the background and the context and introduce P4 symbolic, why we needed the improvements, and then Meghana will actually talk about the ideas that we had for improvement. So our overall goal is to ensure our networks work as intended. And to achieve that, we need to achieve two sub-goals. The first sub-goal is to ensure that the controller actually produces the correct set of table entries that basically correspond to our intents. And the second is that we want to ensure that the switch works as expected given those table entries. And for now, our focus is on the second goal. We want to make sure the switch works as expected. And unlike traditional ways of writing manual tests, which is very labor intensive and hard to evolve once our expectations change, in our team, we basically automatically derive the test from a formal specification of the switch. And as mentioned, we use P4 as the specification language, and it is the job of our team to create these tools that take P4 as input and as output generate a bunch of tests for the switch. And we have been very successful in prefetching bugs before deployments of switches in production. One of these tools that we've developed is called P4 Symbolic. It's a coverage-based automated test packet generator that we use in data plane validation. And by that, I mean, we take the table entries, some table entries, for example, from our switches in prod, and then we give it to P4 Symbolic and give it some coverage goal. For example, we say generate packets that hit all of these table entries that I have in my snapshot. And then P4 Symbolic generates these packets, and then we inject these packets to an actual switch and our simulator and see if the outputs match or not match, and investigate if there is discrepancy. So in this talk, we're gonna dive deep into how P4 Symbolic works. It uses a technique, very well-known technique called symbolic execution, which is again a well-known technique for generating test inputs for a program. I'm gonna demonstrate it here with a very small example. Let's say I'm interested in finding inputs that reach this do-be function. So in symbolic execution, we start with a symbolic input. And rather than taking one execution pass in the program, we actually explore all the possible execution paths in the program and find the execution paths that reach our target function. And then from here, what we do is that we find the constraints on our symbolic input that make that path possible. For example, here, if x is greater than 0, y is 2 times x, and y is less than 10, then we reach this function. So what we do is that we encode this constraint in a machine interpretable form, for example, SMT formulas, and then we use a solver, for example, an SMT solver like Z3, to try to see if this formula is satisfiable or not. The solver either tells us this is not satisfiable, meaning that there is no input that can reach this point in the program, or it gives us some satisfiable assignment that we use as input for our program, that we can be sure that we reach this point. So that's the basic idea behind symbolic execution. There is many variations of this technique depending on the application domain. For example, how you explore the paths, how you keep the state, how you resolve this constraint. And we're going to touch on some of these details here today. So in the context of P4, your input is an input packet. Your tables are a bunch of if-elses, which are connected to each other through a bunch of other if-elses. And then if you're interested in, say, finding input that hits a certain table entry, again, you start from with a symbolic packet as input, and you do symbolic execution. And that's exactly what P4 Symbolic does. To be a little bit more specific, we have two phases. In the first phase, given the P4 program and a set of table entries, we do this symbolic evaluation, as I said, and then we generate what we call symbolic packet trace, which is a SMT encoding of the packet processing execution according to P4 program and table entries. So this is only done once per program and table entries. And then after this, given a high-level coverage goal, and we have a mini P4-based language for describing these high-level coverage goals, what we do is that we cover these goals to a set of what we call a list of what we call packet synthesis requests. Each of these requests provides some constraints for a packet to be generated. For example, one request could be, give me a packet that hits this certain table entry in this certain table, and I want the packet to be forwarded at the end or dropped or things like that. And then for each of these requests, what we do is that we combine the constraints from that request with our, again, with our symbolic trace, and we give it to Z3 to see if it is satisfiable. If it is satisfiable, we extract a packet out of it and return it. Otherwise, we also say that that request is unsatisfiable. So that's basically how P4 symbolic works. And since 2020, P4 symbolic has been the main way and sometimes the only way that we do data plane validation behavior, data plane forwarding behavior validation for our switches and network infrastructure, switch infrastructure products. So there are tens or even hundreds of tests running daily in Google that test the hardware, and under the hood they call P4 symbolic to generate these test packets. So that makes a bit of challenge for us because the type of problems that P4 symbolic is trying to solve, symbolic execution, SMT solving, all of them are NP hard problems, and so they're very computationally expensive. And so if you're not careful about the performance, P4 symbolic can easily become the bottleneck of all of these testing efforts that we have, and at times it has become the bottleneck. So that prompted us to spend some time and resource into improving the performance of P4 symbolic, and Meghana will talk about some of these ideas.
Hi, everyone. I'm going to talk about how we have made the performance of P4 symbolic better. So the first solution that we tried was to reduce coverage, as you have seen, to ensure P4 symbolic works at least in some way. The first, you can reduce coverage by reducing the coverage goals, that is, ignore some expensive tables or entries, or you can say, use a time limit and say, okay, I'll stop my execution after this particular certain time threshold, even if the goal is not achieved. But as one can understand, this is undesirable, but we had to use it as a last resort at times. So the next sort of useful solution is to do offline packet synthesis, that is, use caching. That is, for a given P4 model and a set of entries and a coverage goals, we generate the test packets ahead and then test the switch. And we ensure that we do not allow any code merges till the cache is populated. That is, the cache is consistent with the current P4 model and entries that we have. But however, there are a few caveats. That is, if the time to populate cache is, say, 17 hours, it takes up a really long time to populate it and then test it. And if you have frequent model changes or frequently you update the entries, then when you have concurrent development, then the cache gets corrupted, and this leads to a lot of hazard. This is great. This is better than the previous solution, but let's look at some other better solutions. Next, what we do is parallelization. If you remember this table, the synthesis part of it is for every synthesis request, you synthesize a packet. And if you have n synthesis requests, all of them are independent of each other, and you can parallelize them. As a result, we make the whole symbolic execution and the synthesis packet into a service, and now it can be called for each packet individually. Now we can start a bunch of servers and run these packet synthesis services on the servers and distribute the synthesis requests among these servers. This way, we can reduce the overall time that it takes for synthesizing n packets. Well, however, we notice that even if one packet, let's say, takes 2 to 3 hours to synthesize, that's not great. And for this, so far we have tried everything around the symbolic execution to make it better. Now we've decided that, okay, to go into the details of symbolic execution and make that faster. So as I was mentioned, we'll now look into the symbolic execution part of the service and try to make that efficient. So when we are performing symbolic execution in the P4 program, we maintain a state comprising of two things. One is a guard and a guarded map. A guard represents the conditions that allow the execution to reach this current point. And this gets updated whenever you encounter a conditional or a match condition in case of the tables. A guarded map represents a map from the fields in the header and metadata to an SMT expression. That is, it represents the value of the field at the current execution point. And that gets updated whenever you visit an action. So if you have larger expressions, then it will take more time to solve that expression, and thereby it takes more time in your P4 symbolic tool. And every time you visit an action or a table, every entry, this guarded map, the expression in this guarded map just keeps on increasing. So we want to make, so we'll look at what the current problem is and how we're going to optimize it. So if you take this program, the way the symbolic execution is done without this thing called merge points is you take the conditional, evaluate T1, visit the whole table T1, then visit T3, then go back to T2, visit T3. And as you can notice, T3 is visited twice, and this leads to larger expressions in the state. And if you have a huge P4 program, this just keeps on adding. To optimize this and reduce the size of the expressions, we use something called merge points. In this case, what we do is we take the conditional, we take the visit T1 table, then we visit T2, and then visit T3. And we merge the states after T1 and T2 at this natural merge point that occurs after the if-else branches. And this way, we visit T3 only once. And this leads to smaller expressions. Note that the same state is propagated through T1, T2, and T3. And the same state keeps on getting updated. So this is good. Initially, when it was taking about 17 hours at one point for P4 symbolic to serve on a bunch of requests, now with these improvements, the parallelization merge points specifically, it got reduced to 1 minute. And this is a huge improvement. But so did it solve the problem? As you can see, it did. But we also noticed that as new products came into the picture with many more use cases, it led to more complex pipelines and larger snapshots. This way, the time increased again, that it led to more than 4 hours to serve the same request. And adding more compute servers also did not help. So for this, we'll have to go back and optimize the symbolic execution further. So as last resource, again, we had to reduce coverage, enabled the time-bound synthesis, again, relied on offline synthesis. And as a result, we want to make symbolic execution efficient. So the next thing that we tried is called guard factorization. Okay, let's take this example where you have a sample table of 3 entries. You have the state S0, that's before you start visiting this table. So S0 comprises of a guard and a guarded map. After you have evaluated this particular entry, the state changes to S1. Initially, the guard would look like it's just true, and guarded map would be some variables, free variables for input and output. After you've evaluated the first entry, the import guard would change to, okay, it's true and input should have been 1. And the output would say the action corresponding to the output would be, if it's true and u is 1, that is input is 1, then set the output to 1. That is if then else, it's an if then else construct, or else let it be whatever it was before. Now you use the same state as 1 and evaluate the second entry to get S2. It adds on to top of the previous expression that you have. Then evaluate the third state, third entry, and you get this huge expression as you can see here. And if you have 1,000 entries and many more tables, the expression just keeps on getting bigger and bigger. So how do you compress these expressions? How do you make them better? So we use something, we optimize the symbolic execution at this point, where you have this global state. And whenever you evaluate each of these states, you create a local state. That is, you first enter the first entry. The local state would say, okay, this I'm just directly going to update the guarded map to whatever the action was. In this case, output to 1. And I do not care about what was there previously in the global state. I do this for every entry, and I create local maps for every entry. Along with the global state and these local states, with the merge conditions, that is the match conditions here, I would merge them to create the new global state. This way, we would have a much more simpler expression. And because you're not building on top of a global state, we are having simpler local states, which we merge with a global state to have a simpler expression. So as you can notice, the u not equal to 1, u equal to 1 is only present once in the right-hand side, but it was present 3 times here. So every match expression that you would have had gets repeated I-1 times. In the new optimized flow, it appears only once. This way, we were able to reduce the complexity from O of n squared to O of n, where n is the number of entries. And this led to smaller expressions and thereby faster SMT solving time. We noticed that when we ran this on many of our products, it led to 800x speed up, which is crazy high. And this also increased developer velocity. We were able to test a switch with larger snapshot and also expand our coverage goals, as you can see. So far, with all the improvements that we've had, we were first initially able to get 1000x speed up, then decreased a bit, and then later 500x speed up. All in all, about 6 orders of magnitude speed up with all the optimizations that we've had. So this is the current state of the P4 symbolic. But what do we want to do next? We want to improve our coverage codes. Why do we want to do? Let's look at one case where you have an ACL table and the coverage code says, give me packets hitting all the table entries. And P4 symbolic gives one such packet, and it's an IPv4 packet. But then in the production scenario, if I had an IPv6 packet, this probably would have failed, because the scenario is that it would fail in case of an IPv6 packet. And we could have missed this bug if P4 symbolic only gave the IPv4 packet and did not give an IPv6 packet during testing. So we do not want to be in such a scenario. How do we make it better? We can expand our coverage goals. Currently, our coverage goal says for every entry, generate a packet that hits this entry. But now we could say for every entry and every header type, generate a packet containing this header and this hitting this entry. And you can keep on increasing this every time you think of a new criteria. But this will lead to many more requests and slower packets in the system, and you may not be able to correctly encode your coverage code as well. So the next solution, which is to use a path coverage, which is the ultimate form of coverage. Path coverage means, let's say you have 2 tables. A packet could take the first entry of the first table and second entry of the first entry of the second table. It could take every row from the table 1 and table 2. And this way, the packet could have taken 9 paths, that every possible scenario of packet flow will be tested in this way. If you had 1000 entries per table and 3 tables, that's just a billion paths, and this is exponential. So this leads to a path explosion problem. You cannot cover everything when you're doing symbolic execution. So is there a hope here? So the hope is that we can prune paths as you go, because not all paths are valid. What do I mean by this? If, let's say, the first table sets an egress port, and the second table matches on the egress port, then the packet would have taken only the first path, 5. It would have matched on 5 and taken the first entry 5. It wouldn't have matched, this is a valid path, but it wouldn't have set on 5 and taken matched on 10, as shown here. This is an invalid path, and we do not have to traverse those paths when you're doing symbolic execution. So there were only 2 out of 9 valid paths, and this way we can prune the paths to have better, faster performance. We tested this on one of the switches, and out of the 10^14 paths, we were able to, there were only 2 million valid paths, and thereby we can generate 2 million packets and do not have to traverse all the 10^14 paths. However, this still takes 8 hours, which is huge. So can we do better? The observation is that every time you generate a packet, you have a bunch of calls to a Z3 solver, and if you can reduce those, then it can lead to faster execution times. And we plan to explore ideas from the literature that address this problem, and hopefully it will improve our coverage goals as well. The future, Ali is going to talk about.
So yes, thank you. Quickly looking towards the future, if you remember, I said we have 2 goals, and so far we've been focusing on the second goal. But even if you make sure the switch works as expected, given a set of table entries, you still haven't made sure that your controller is producing the correct set of table entries. So that's what all of these network verification tools and systems are trying to address. And in essence, what they do is they also do some form of symbolic execution just at network level to verify properties about the network. And actually in Google, we do have such a system in use. However, this system that we have in Google was developed before we had P4, and similar to many works in literature, these network verification tools usually use a hard-coded incomplete models of the switch. So they don't have any guarantees on the fidelity of their model. The tool may tell you that, oh, your table entries are correct, but it gets it actually wrong because it has modeled the switch in a wrong way. So that's one problem. The second problem is that because they have hard-coded models, they're hard to evolve when we add new features to the switch. So since we're already working on P4-based symbolic execution in a single switch, a potential future direction for us is to expand this symbolic execution based on P4 to network of switches and do this kind of network verification type of stuff. The good thing would be that because of all of these, because we have these P4 models and we already do this data plane validation, so we have a high assurance that our model has a very high fidelity and corresponds to how the switch actually works. Also because, again, it's not a hard-coded model, it's based on P4. The evolution would be effortless because the tool will be parametric on the P4 model. So that's all we had to say here. Thank you very much. If there's any questions.
Quick question. So very fun talk. Thank you. So when you, in terms of complexity, so slowdown and everything, what do you think is the biggest contributor? Is it the density of the program you're modeling or the number of entries you're trying to work with? So do you have an intuition?
So we are using, our models of our switches, because we model the switches after our use cases. The switch may be very complex, as mentioned in the last talk, but our use cases are going to use only very few features of the switch. So our models are actually very simple. I think the biggest contributor is the number of table entries. And even that is not high. I think so far, our biggest contributor to bad performance was the inefficiencies that we were talking about in SMT, how we generated the SMT formulas. I think we got rid of all of that inefficiencies. So in the future, I think, probably the number of table entries will be the contributing factor. Yes.
All right, thank you.